and so on. In fact, James, you might be interested. Next week, we have a guest lecture from Intel, a friend of mine who actually develops, who leads the effort on advanced displays for Intel. And he's done this for many years. So he's going to give us a lecture. And it's also going to be a department seminar next Thursday. So you'll get an email. Everyone will get an email. So everyone's welcome. So it's relevant to some of the stuff that you will talk about. Also, very, very interestingly, I know Facebook and Google, they have been pursuing this micro OLEDs for augmented reality and virtual reality displays. I'm actually involved in some of these projects, but I can't really talk about it because of confidentiality agreements. But yeah, lots of very exciting stuff happening, particularly related to optics. So it's very relevant that you are talking about this stuff this week. Okay, why don't you go ahead and share your screen? And same as before, feel free to ask questions on chat. I'll try to monitor it. And also, feel free to interrupt James as well. I'm sure he doesn't mind if you have questions. The goal is for all of us to understand very, very well. Okay, James.
Yeah, I can't see your faces or the chat, so you'll have to just like shout me down to get me to stop.
I'll monitor the chat. I have the same problem, by the way,
okay.
When you share the screen. So I'll monitor the chat, but again, feel free to unmute yourself and ask if you have questions. Okay, I'm going to go on mute. You're on, James.
You can see my screen, I hope?
Yes,
okay.
Works.
Well, normally I do a little section where I describe myself, but I guess Rajesh just gave me the introduction already. So I did my PhD here at the university. I graduated in 2011, and it was on light trapping for silicon solar cells. After that, I worked for a startup called Terahertz Device Corporation, where they were making infrared LEDs. And it was specifically because I did all this light trapping, he wanted to use that skill to do light extraction out of the LED. So this makes kind of a fun back-to-back pair of lectures where the first one is doing everything we can to get light into a semiconductor and harvest the energy. And then you have the exact opposite problem with LEDs, where you're putting energy in and trying to get as much light out of them as possible. So like to say, the same physics, but different directions. So I was a research associate for a few years with metallurgical engineering. So that's me there with our eddy current separator, pulling copper out of scrap metal. And so my background is mostly electromagnetics with a strong emphasis in numerical methods, and just modeling stuff is my favorite thing in the world. So let's just kind of define what light trapping is. And it's pretty self-explanatory. You have some physical geometry or something in space, and you're shining light on it, and you want to trap light within it somehow. So you just define light trapping as the energy absorbed within it divided by the energy that's actually illuminating the object. And you can notice there's kind of three things that will happen here when you shine light on something. So you can hopefully see my cursor here, so I can point at stuff. So obviously there's reflections just by that dielectric boundary. Some light will strike and then bounce away, and so you can call that scattering. Then some of that light will transmit inside the device and bounce around and maybe get absorbed eventually at some point, or slowly attenuating. There's two perspectives here. You have the classical electromagnetics, where it slowly just attenuates as it bounces around. Or you can think of it quantum mechanically as a photon bouncing around until eventually there's some finite probability of it getting absorbed at any given moment. And it will either eventually get absorbed, like say, you imagine the photon banging around until it gets absorbed here, or it might escape out the other side through a transmission effect. Okay, so it's a nice straightforward mathematical definition. We call it light trapping efficiency, or you can also call it an absorption factor, which is just energy absorbed divided by the energy that you illuminate it with. So what are the many applications for light trapping? Because there's more things going on than just solar cells and optics. So solar cells are obviously like the one we care about most right now, but you can think about this in terms of broader applications, like the classic stealth bomber, where you're shining radar on the thing and you don't want any echoes to give away your position. So they have that fancy magic stealth paint that's supposed to absorb all the radar light that strikes it. So you can think of that as a form of light trapping. I want all the light to just get sucked in and trapped and not bounce away. An anechoic chamber you can think of as another application where light trapping is important, because I'm illuminating an antenna and I want to measure its directivity. And some of that light is going to scatter away and hit the walls and bounce back and corrupt my measurement. So that's the name, anechoic, no echoing, non-echoing. And so all that magic foam around the walls, you can think of it as a kind of light trapping, where all the light that strikes it, I want to be absorbed and not have it bounce away. So let's kind of talk about the broader economic picture of solar energy. So obviously, as the world industrializes, especially the third world, the demand for energy is skyrocketing across the world. And there's only so much fossil fuel left on the planet to burn. Yes, there's a lot of it, but it is a somewhat finite resource. And even if, hypothetically, we could dig up all the coal and all the oil on the planet, hypothetically, we may only be able to last for a few hundred years at this rate. Whereas the sun is just going to burn for the next few billion or so. So that makes solar energy somewhat desirable in the long-term sense. There's also the glaring problem of climate change that we got to worry about, and carbon emissions, which you don't have to worry about with renewables like solar energy. So this is a very fun map here I like to show, put together by NREL. So that's the National Renewable Energy Laboratory. So I think you can kind of think of them as a mini National Science Foundation, where their goal is just promoting research in renewable energy. So I think they're like a subset of the Department of Energy. And this is a fun graph where it's just imagine, all the average daily light striking the United States. So I think it says annual average solar resource. So you take all the sunlight shining onto a particular square meter of dirt within the continental United States here, and just average the total kilowatt hours per day across an entire year. So I think it's accounting for, in summer, this will be hotter, and winter will be colder, and you average it all out. And so, of course, there in California, New Mexico, and Nevada, it's super, blazing hot desert. And as you go northerly in latitudes, you get less of a solar resource to work with. And on top of that, I like to show this picture of this solar farm. I have no idea where that is. I think that's like in Europe somewhere, for all I know. But it's just to kind of illustrate, like, the technology exists. People have already built these solar farms, and they're building more every day. So why aren't we just flooding the Arizona desert with solar farms to harvest all of the sunlight and satisfy all of our energy demands from now until eternity? So normally I ask this as kind of a hypothetical, but it's a little hard to do when all your faces are buried. So we'll just kind of jump into it by saying there's obviously a lot of practical limitations to solar energy. Like, as desirable as it is, there are certain just practical limitations, right? Like, for example, if you're out in Alaska, you don't have a whole lot of sunlight to work with. And it's very hard to get energy from New Mexico out to Alaska, say. So simply transmitting the energy is a difficult problem if you're in a place where there isn't a whole lot of sunlight. You also have the problem, of course, where the sun doesn't necessarily shine all day, every day. You have to deal with day-night cycles. So storage of that energy is another giant hurdle. And then you have to deal with the fact that there are cheaper alternatives to energy available. Just because the solar resource is renewable and carbon-free, that doesn't necessarily make it cheap or cost-effective compared against just burning coal and powering generators that way. So yes, it's there. We're pushing in that direction, but there are certain practical barriers we have to overcome before we can really create a truly renewable grid. So just for comparison, I just looked this up today. Like, what does the average American household consume per day? And it's about 30 kilowatt hours. So you look at the graph here, you can see, in some of the hotter regions of the country, it's on the order of about 5 kilowatt hours per square meter per day, 5 and above. So that kind of gives you a sense of, hypothetically, if I just had like 5 or 6 of these panels, in principle, there's enough energy on that square footage, that square, I guess, meterage, that area, to power my home throughout, or to power all of my energy needs. in principle. In practice, though, there's obviously a lot of issues in terms of how much efficiency you can really get out of a solar cell. So just because there's 5 kilowatt hours per square meter per day landing on my rooftops, that doesn't mean I can actually harvest all of that energy and make good use of it. So we'll talk about that now, just in terms, or in a bit, some of the practical barriers to harvesting that energy and turning it into useful work. So one of the major barriers historically has just been the cost of solar cells. Yeah, they're really cool and neat, but the dollars per watt investment you have to put into installation of one of these facilities is huge, or at least it was huge. And in the last 10 years or so, it's come down a lot. And in fact, it kind of follows its own little Moore's law kind of graph here. So what you're seeing is module ASP. I forget what ASP is. I think it's the total cost of an actual like integrated system. So you have the solar cell, then you have the power inverters and the labor involved in just hooking this sort of thing up and connecting it to your regular grid and all that kind of stuff. So got to bear in mind, it's not just the solar cell, it's the solar cell and the mounting and the integration of it into your grid all add together to create costs. So it's kind of neat. It's like I said, it's almost like this Moore's law thing, wherever you like, well, it's not exactly, because you see it's not a perfectly uniform trend here, but you can see as the economy of scale picks up, the cost has come down dramatically in these modules. So you see it's normalized to 2016, so it's inflation adjusted. And one of the magic barriers that we crossed in about 2016 or so was $1 per watt. That was kind of the threshold where installation of a solar cell or a solar energy panel grid became really, cost equal to that of just like burning coal and gas. So we've crossed that barrier and we're still getting cheaper and cheaper. At some point, I'll need to upgrade this. This was 2018 I gave this talk. So that's the latest data there. So it'd be interesting to see how we've come in the last 3 years as well. But assuming these trends continue, it's going to get cheaper and cheaper still, which is good, because the cheaper it gets, the more people are going to invest in it and install these systems. Which means the more demand we get, the more incentive there is to streamline their production, and you get this nice feedback cycle there economically. So the economics used to be a major hurdle, but that is coming down dramatically. So let's talk about just the raw physics of constructing a solar cell and harvesting energy from it. So it helps to just kind of create this idealized solar cell and think about the anatomy that goes into it. So basically you have a PN junction made out of some semiconductor material, and you have a top contact and a bottom contact, and you're shining light on it. So you just say incident photons are raining down from the sky, and they come in, and one of those photons strikes an electron and creates an electron hole pair. And then that electron and that hole have to meander around through some just random Brownian motion until eventually colliding with one of the contacts. And then you have this excited electron that can finally be used to do real work. So you create that photocurrent in that sense. So now we got to ask ourselves, okay, that's in principle what's going on. So what are all the things that could go wrong in this, right? Or what? So first question, what do I make my solar cell? In fact, like just the material itself is a major question. At least 10 years ago, there was kind of a big debate of what we're going to make the solar cells out of. So silicon has always been kind of the dominant contender, but there were other materials on the market for a long time. And in fact, the first material to break the $1 per watt barrier was a solar cell made out of cadmium telluride. So there's a lot of, so I think Mike Scarpola's group, he spent a lot of time, and I think he still is, where he's investigating copper zinc tin sulfide solar cells. So silicon is great, but there are other contenders out there. But for now, silicon is definitely the dominant material on the market for a number of very clear reasons. So in particular, the abundance of silicon is a very powerful selling point, because if you want to flood your infrastructure with solar cells, you're going to need a gigantic stockpile of raw material. And it sounds kind of obvious to say that, but not all materials are created equally in this sense. And in particular, the cadmium telluride was made out of what are called secondary metals. That is, you don't mine cadmium per se, you mine something like copper, and then cadmium just happens to fall out of the process as a result. And so this was a big deal 10 years ago where people were running the numbers and they're like, physically isn't enough cadmium and tellurium in the Earth's crust to satisfy all of our energy needs. So just because it was nice and cheap and efficient didn't necessarily mean it was this magic silver bullet that would solve our problem. So the sheer abundance of the material is something you have to consider if you're going to create an electrical grid out of it. Other fun factors: silicon is generally not very toxic. In fact, something like 25% of the Earth's crust is already some sort of silicate material anyway, which again, you compare that to cadmium telluride, where cadmium is a heavy metal and you don't necessarily want that stuff getting into your groundwater. Which is bad because these solar cells are going to have a finite lifetime, right? I use it for 20 years and eventually the thing just wears out and you got to dispose of it somehow. And you can't just toss it in a landfill without necessarily thinking about the material in there and what it will have impactfully on the environment. So then you have issues like the band gap, right? So it's not all materials are going to have the same band gap, and some band gaps are better or worse than others. By sheer happenstance, silicon happens to be very close to the ideal value given the limitations of our sunlight. And just as luck would also have it, silicon, the industry around silicon had like 40 years of development just in the computer chip industry, thanks to companies like Intel, who worked very hard to turn silicon into microprocessors. So we're already just kind of very good at working with silicon on an industrial level. So for that reason, if you go buy a solar cell off the shelf, it will almost certainly be made out of silicon. So let's talk a little bit now about sunlight itself, okay? Because there's a lot of subtlety in the nature of the photons that come raining down on us from the sky. So you have what is called the air mass zero spectral reference. And this is basically what you would measure if you launch a satellite into space and put a giant spectrometer on it and point it at the sun. This is the sort of the average spectrum you would get from the sun day by day. It's that black curve there. And you notice there's all these sort of absorption lines there from all the spectroscopy and quantum mechanics happening. But you notice if you do a sort of a curve fit, it matches very, very well with a black body radiation spectrum, somewhere on the order of 5,000 to 6,000 Kelvin. So fun fact, that's kind of also how we know how hot the sun is, at least around the surface. So what you then do is you add up all of the energy in that curve, because you notice it's a function of wavelength, right? So you see solar irradiance, the units are watts per square meter per nanometer. So not all wavelengths are created equally in that solar resource. So what you do is you take the total area under that curve, and then you imagine a 1 square meter aperture collecting light, and you would collect 1.366 kilowatts in that square meter aperture. So that's kind of how you interpret this curve. Now, fun fact, we don't actually live in space, obviously. There is an atmosphere between us and the sun. So what you do is you stand outside on noonday and you stare straight up, and there is exactly 1 atmosphere's worth of air that the light has to travel through before it reaches your face or reaches your solar cell here at the ground. So what that means is you lose a bunch of energy just in the spectral absorption in things like carbon dioxide, and in particular, like the water vapor in the Earth's atmosphere tends to have a major effect. So that takes a huge bite out of your spectrum there, as you can see in the red curve. Only really there's more to it than that, because the sun isn't exactly like straight above us. We are actually in the continental United States, which is about 37 degrees upwards and away from the equator. And then the Earth is also tilted and wobbling as we go around the sun. So sometimes, we're a little toward the sun and the Earth will be tilted away. So you have to average all of that stuff out sort of across a year. And so that is where you get this air mass 1.5, because the sun isn't on average perfectly straight up. It's tilted a little bit. So it's not just going through 1 atmosphere, it's going through on average like 1.5 atmospheres. So that's what the red curve fundamentally represents at the end of the day. It's that air mass 1.5, and it's kind of considered the universal standard of about the average spectral resource you would get somewhere across the continental United States. And again, this will change depending on whether you're up in Michigan or down in Arizona. So think of it as just an average, but you need some kind of standard if you're going to quantify the performance of a given solar cell, right? Because you could hypothetically optimize a solar cell to work very well up in Maine, and it may not work so well if you take it down to Arizona, say. So you just need some kind of standard reference to quantify the overall performance. So because you're losing a bunch of energy in the atmosphere, that 1.3 kilowatts get reduced down to about 1 kilowatt per square meter when you take the total area under that red curve. So fun fact, it just by happenstance, I think they probably deliberately tweaked it a little bit just to round it to exactly 1 kilowatt because it makes things nice and easy. So now, we have to think about this a little more quantum mechanically, right? So just because I have 1 kilowatt per square meter raining down on me, that does not mean I can actually harvest all of that energy, because any given semiconductor will have a finite band gap or a fixed band gap. So what that means is all the photons with an energy below the band gap cannot be absorbed. You can't do anything with them. And all of the photons above the band gap in energy, those are the ones you can actually harvest. So what I'm doing here is we've converted the chart rather than watts per square meter. It's more instructive to think of it in terms of photons per second per square meter per nanometer. And then we're going to chop it in half. So the band gap of silicon is right there at about 1120 nanometers. And all the photons above that wavelength are now completely useless to us because they cannot excite an electron hole pair. So I'm just going to click the button and you throw them away entirely. They're all totally useless. I can't use them. And you notice I am now down to about 811 watts per square meter in terms of usable power if I'm using a silicon solar cell. And this will change a little bit depending on your actual semiconductor material. And we're actually not going to quite get into the subtleties of that, because you notice what happens as I go higher, lower in band gap, I will capture more photons. But then there's a problem where just because the photon has a high energy doesn't mean you can actually harvest it all. So the idea is, so say I have a band gap of 1 electron volt, but the photon is 2 electron volts. So yes, it will excite the electron up to 2 eV, but then it'll immediately decay down to an energy state of 1 electron volt of excitation. So just because there's 800 watts usable, I can't actually use even that. So you have to count each photon, and each one has a fixed amount of energy that is the band gap of silicon that I can harvest from it. And all the rest of that is now going to be wasted even more. So you look at the band gap of silicon is, I even wrote it down, 1.1 EV, electron volt. So that is the absolute maximum energy each photon can give me. Even if it's a 2 EV photon, I can't harvest it. So then you impose that upper limit and you integrate across the spectrum yet again. And what you find is the total usable power I can get out of a silicon solar cell is almost 50%, 48.8. But then it gets even worse than that, because just because I have an electron hole pair with some energy, there are still some practical limitations that you have to deal with in terms of just delivering that energy to a load and doing work with it. So I haven't seen quite as much of an analysis or derivation of that. It is in the textbooks on most solar energy, but that then imposes yet further limitations. And it brings us down to about 32%. So I don't have a derivation or proof of that, but you can research that for later. So this is called the Shockley-Queisser limit. It says, given sort of the solar resource, the spectrum that we have from the sun, 32% is the absolute maximum efficiency you can ever hope to conceivably get out of a silicon-based solar cell. Okay, and that is if everything else in your system is absolutely 100% perfect. So you can kind of take that 32%. If you can get a 32% efficient solar cell, you have the absolute maximum efficiency that nature will allow, essentially, given a single band gap silicon cell. So let's kind of using that as a benchmark. This is a really fun slide I like to show. This is in 1999, this particular design, it was a paper published, it was the world record holder for efficiency in a silicon solar cell. And they got it up to about 25%. So I don't know how much that record has really been shattered ever since, but if I had to guess, the best you could probably get is maybe 26 or 27. I don't know. But that'd be interesting to hear if anyone's, I know people have beaten it, but when they do, it's usually by like 0.1% kind of incremental improvement. So that'd be interesting to see what the current world record holder is. But this was just nice because it shows you all the steps they took to try and increase their efficiency. So you can see they've got this double layered antireflection coating. They got these weird inverted pyramids trying to get light into the cell. And it was 400 microns thick in this particular device. Although for a more commercial based device, you usually get somewhere in the order of 150 to 250 microns. So you also notice that to create something like this, they are using very high quality crystalline silicon. And you get these little modules that are 100 square centimeters each, and they all have to kind of be soldered together, right? So what you get is if you want to buy something like this on Amazon, say, so or I guess I should also mention, there's a slight barrier between what someone can do in a laboratory versus what you would even buy off the shelf. So I think it was like 2 years ago, I went to Amazon and just looked up, high efficiency silicon solar cell, and that's the panel you could get a couple of years ago. So you see it's a crystalline silicon, it's a 100-watt solar cell, and you do the math on their pricing in the area, and you find it's about $1.8 per watt with a net efficiency of 15.5%. So that's yet another thing to bear in mind. Just because someone in a laboratory could get 25%, that doesn't mean it's very economical to shoot for that, right? So a lot of corners get cut when you actually build something like this and try and sell it. So a quote unquote high efficiency solar cell on Amazon will barely be 15, 16, maybe 18% right now. That may have changed in the last couple of years, but that's what it was like in 2018. So why is the light, what are some of the reasons we can't trap the light in here? So there's a number of things happening in terms of our efficiency loss, right? So it's not just light loss, there's the efficiency as well, with a bunch of competing factors we have to deal with. So first things first, let's just imagine I have to trap the light. What happens after I trap the light is like a totally secondary issue. But first things first, you have to trap the light somehow. Okay, so how do I lose light? Well, the first obvious reason is, so you notice I've broken up. I have a PN junction here. We'll assume it's crystalline silicon. Some light rains down, and immediately, because you have a dielectric boundary, you get a reflection. So that's that surface reflection right there is one major source of inefficiency in a solar cell. You also have the contacts here, the metal contacts. You have to cover it with some sort of contact to harvest the electrons and holes. So those will block light and physically scatter around. In fact, if we go back, you can see these little traces here. And if you zoom way in on that, you'll see like these little metal fingers covering the solar cell. And they necessarily impose limitations on your efficiency, right? So you imagine that little metal contact now, that's blocking light. And then you also have the problem where light may get in, propagate all the way down, strike the bottom contact, and come all the way back up again and fly out without ever even being absorbed at all. So I guess you call it transmission loss, I suppose, or just back and forth, that kind of thing. So how do we mitigate all of these issues? Well, the first thing is you want to minimize the surface area of your contact. So that's why if you zoom in on a solar cell, those little traces are very tiny, and they're trying very hard to cover as little area as they can with those contacts. But you also need to cover a large area of the surface just to collect the electrons in the hole. So you got to be careful with that. Then you put on an anti-reflective coating. So that will minimize some of the surface reflections off that, that initial bounce. So this little guy here, you can minimize that loss by using like a layer of, say, silicon nitride. But then you still have to deal with the problem of light may just go all the way through, hit the back contact, come all the way back out again, and never once encounter an electron hole pair. So how do you mitigate that? Well, you could make it really thick, so that increases the probability of capturing your photon. But then you have to be careful with that, because now I've created the electron hole pair, and where are they going to go? So if you make it too thick, yes, you'll trap light, but you won't be able to do anything with it because you get recombination loss. So this is one of the frustrations where the thing you need to trap light is completely at odds with the thing you need to collect the particles after you're done. But we're just here to talk about the light trapping and not necessarily worry too much about sort of the quantum mechanical effects of what goes on afterwards. So one of the most important parameters of any given material is this idea known as absorption length. So you just imagine shining a photon through some material, and in any given moment, there is some probability that it will be absorbed. So how much material does it have to go through before it is absorbed with a 1/e length? Right? So we use e because there's all these exponentials showing up in the math. So the absorption length is defined as the 1/e distance of probability, which evaluates about 63%. So that's what these curves are here. So just for kicks and giggles, we're comparing something like gallium arsenide, which is a popular material for photovoltaics, and we have crystalline silicon. So gallium arsenide is a direct band gap semiconductor, which means as you get really, really close to the band gap, you have very short absorption lengths, and then all of a sudden it's it shoots off to like infinity, right? So as the photons cross that boundary, they stop absorbing basically. Whereas crystalline silicon has this much, much smoother curve here. And you just look at the graph, something like an 800 nanometer photon in gallium arsenide has an absorption length of about 1 micron. And this is a logarithmic scale. So you compare it to silicon and it shoots up to almost 10 microns there. So we really want to use silicon. As much as I would love to use gallium arsenide, crystalline silicon just has too much of economics working in its favor. Now, another major problem is the physical material of silicon is often very expensive as well. So I feel weird talking about it now because this was a big deal 10 years ago where if you were to construct a solar cell out of something like a 200 micron wafer of silicon, that raw silicon cost was as much as like 40% of your entire system, just the raw silicon. So there was this huge push to try and make solar cells thinner. I don't know how relevant that is now, but this is kind of the crux of the physics involved in light trapping here. So we'll get into that in a moment. So this motivated the idea of, instead of having these hundreds of microns in my crystalline silicon, because you need that in order to capture all those photons, what if we just shrank them down to a couple of microns? So the idea was, let's give up some efficiency in exchange for cheapness. And so thin film solar cells are often very, very cheap, but you take a major hit in your efficiency. So this was something you could get on Amazon, again, 2018. And you notice it's made out of amorphous silicon. So that's what that ASI means. So that's a whole separate issue of amorphous silicon versus crystalline silicon, which we're not going to quite get into. But you notice it was only 6% efficient. So you need like twice as much or 3 times as much of this to compete with the expensive stuff. But you notice the actual cost per watt came down. Before it was $1.8 per watt. Now it's 1.2, just because I went thin and dirty with my materials. So just because I took a hit in efficiency, it is that much cheaper anyway. And as long as you don't care about real estate, we'll just make 3 times as many of these to make up the difference. So you're kind of trading space for cost in this sense. Yes, it's cheaper, but you need more of them to capture and harvest the same amount of light. So the idea of thin film is, instead of being hundreds of microns, let's make it down to 1 or 2 microns instead to save our material cost. So this is a nice little graphic to kind of illustrate the difference that makes in terms of my absorption length. So using crystalline silicon, it has an absorption length of, about a micron or so at different wavelengths. So here's a green photon, say. You can imagine shining a green laser beam on this little slab. So it's 2 microns of silicon. And you see at 500 nanometers, it has this nice, strong attenuation, right? So over a distance of, say, 2 microns, I will absorb 95% of all the photons in the 500 nanometer spectrum here. But you just go up towards the red a little bit, 800 nanometers, and the difference is very dramatic. Now it needs 10 times as much thickness to get that same 95% absorption. And so I'm sacrificing a huge amount of my efficiency in those long wavelength photons. And remember, the band gap for silicon is way out at 1120 nanometers. So you're losing a sizable chunk of your spectrum by going thin. So what can we do to kind of make up the difference there? So this brings us to this idea of light trapping, which will kind of helps to understand it by doing a few toy models, say. So let's sort of quantify what's going on and see if we can visualize it on the spectrum here. So this is a model I put together where you imagine a 1 micron slab of crystalline silicon, right? And then you just calculate the total absorption of sunlight in this thing, or of photons, you could say, just by using basic electromagnetic field theory. So this is all closed form calculations on this model, and we're assuming a perfect reflector at the bottom. So that's perfect electrical conductor. So no loss in the bottom contact here, and illuminating it from the top at normal incidence. So the question then is, all things being equal, how much light will physically be absorbed in this kind of system? So what happens is, you shine light, I get a little bit of a reflection. Some of it transmits through, bounces back. Some of it then transmits out again, and some of it will bounce back and forth, and you repeat forever to get some net absorption on this thing. So here, this dashed curve here, this represents our sunlight. You notice, again, it's photons per second per square meter. And the red curve is the actual absorption of photons in this particular system. And you see this weird effect where it just kind of goes bonkers. So what you're seeing is at some frequencies, that back and forth reflection is actually destructively interfering with the initial bounce, so that I get just no reflections at all, and everything just kind of gets trapped inside here. But then the price of that is you move off the frequency a bit, and the opposite will happen, where now they all constructively interfere and maximize reflections. And that's why I get a minimum in my absorption. So that is called Fabry-Perot resonance, by the way. So that's a nice sort of baseline model for comparison. And if you add up the total area under the red curve and compare against the black, you get a total light trapping efficiency of about 27%. So obviously that's pretty terrible. So what can we do to make up the difference? So the first step is you want to add an anti-reflective coating. Usually silicon nitride will do that. And in this case, we're doing a completely idealized model. Okay? So it's not even a real material. So it's perfect anti-reflection at all frequencies. So you see how it sort of smoothed out all of those resonances, because what you're seeing is light comes in, propagates down, strikes the back contact, comes back up and leaves out the top again. So for very short wavelengths, I'm getting almost perfect absorption. Then you see how it kind of splits around 500-ish nanometers, where all of a sudden I'm not absorbing super well. It gets worse and worse and worse as I go longer in wavelengths. Even so, I still get a good improvement. My light trapping efficiency went up from 27% to 40%. But I still need some way to trap all of those longer length photons. So what can we do to make up that difference? So this is where you get this notion of path length enhancement, right? So the aha moment for that is to just say, well, just because I have only 1 micron of thickness up and down, what if I could somehow coax my photons into propagating left and right? Because I essentially have infinite distance along these directions. So if I can somehow steer the photons sideways, I have all the material in the world for them to go through and maybe get absorbed. So what you do is you roughen up the texture on the top and bottom of your solar cell, and you get this scattering effect, where instead of just going straight up and down, I get a little bit sideways. And just by that mere virtue of going a little bit off axis of it, I now have to propagate through more material before I can fall out the other side. And if I add more scattering again at the top, I can try and get them to bounce and get trapped bouncing up and down. So the idea is the total path length is greater in length and thickness than the actual cell itself. So, or the photon will end up propagating through a greater distance in this material. So the general term for that is a path length enhancement. And the idealized best you can do, so we'll derive this later. So you imagine just perfect Lambertian scattering at both surfaces. And it turns out you can get upwards of about 81% for a 1 micron, or 81% light trapping efficiency for just a 1 micron cell of crystalline silicon, which is pretty good. It's not bad at all. And so you can imagine if I maybe just go to 2 microns or so, I might get up to like 90, 95%, say. So I don't have to get very thick in order to trap essentially nearly 100% of the photons if I am clever with my scattering inside to sort of trap the light. So this is called the Lambertian limit. the ergodic limit or the Jablonovich limit. I've seen all three of these in the literature. I think Jablonovich is common because I think he did a paper back in 1982 here, where he kind of derived this limit for the first time and kind of set a standard for what you could really do in a thin film of silicon or solar cells. So again, we'll derive that in a little bit. So this notion gave birth to this whole burgeoning field of light trapping in thin film silicon solar cells, and for about a half a decade or so, just people were just publishing paper after paper of all these wacky ideas to try and scatter light within solar cells. So my personal favorite was the plasmonic gold nanoparticles, which was this huge deal at the time until you think about it for 2 minutes and you realize, hold on, you're putting pieces of metal that scatter light away. That doesn't exactly make a whole lot of sense. So, but then you can see how people are putting these little diffraction gratings in, these little pyramids, and scattering all over the place. And people are just reporting all these wonderful improvements along the way. So this is where I kind of came in and did a lot of simulations to show how to trap light as well. In particular, my big contribution was saying, what if we embedded a particle inside the solar cell so that light would come in, scatter off the particle, and then bounce around? So all of this talk about light trapping, you need a language for talking about it in a nice intuitive way. So I found a very obscure textbook back in the 80s that introduced this idea. I think it's very effective at just giving us a nice intuitive grasp of, or intuitive language for talking about light trapping. So what you do is you imagine just a slab of material with some width W. Okay, yeah, and so it could be a micron or 2 microns. You imagine some light striking it from the left, and maybe there's a reflection, and then it propagates through and gets absorbed before falling out the other side. So for the sake of argument, let's suppose there is no reflection here, right? There's a perfect anti-reflective coating on both sides. So light comes in, propagates through, and then leaves. So what is the total absorption of light inside of this little slab? Well, it's the incident minus the transit. So you have light comes in, light leaves, and you take the difference, and that is the absorption factor there. And since the physics requires that it follows this sort of exponential decay, you can model the transmittance out the other side as this e to the minus alpha W, where alpha is the attenuation coefficient or the absorption coefficient for that material. And again, this will change with frequency, so you got to be mindful of that. So we call it the Model-N Slab for no reflections. That's what the reference called it. I should put a citation here sometime for that if I can find the book. So what that means now is I imagine light propagating through some particular distance of this material, and I'll get some absorption factor to go with it. But you can also think about that in kind of the opposite terms. Is given some solar cell with some particular geometric arrangement, I have an absorption factor A. What is the equivalent thickness of this Model-N slab that it would have to propagate through to achieve the same result? So what you do then is imagine A is sort of some fixed parameter from your solar cell, and then I calculate the distance of this equivalent slab that it would have to propagate through, and that is called the equivalent path length of your particular solar cell here. Okay, so again, this is just an idealized model to think about the quality of your absorption in terms of a simple distance, right? So more distance in this Model-N slab means more attenuation or more absorption, or equivalent, you could say the better I'm trapping light, the greater the distance of this equivalent slab I can describe it in terms of. So you can think of it as like a language for describing and quantifying light absorption. So let's do some fun little calculations. So what you do is you start with that simple model again with no reflections, or I can put an anti-reflective coating on. And intuitively, we'll start with the case of imagine that anti-reflective coating where light comes down, propagates through 1 micron, reflects, and then propagates back again. And it would travel through a total distance of 2 microns. So you'd say if I had a perfect anti-reflective coating here, the equivalent path length of that 1 micron slab is 2 microns, or you'd say 2W here in this case. So that's the capital N means with like no reflections here. But if there are reflections now, you get these Fabry-Perot resonances, and you can actually quantify them in terms of the index of refraction for this material. So fun fact, the peaks of that Fabry-Perot resonance are scaled by the index of refraction there. So you take that 2W there, and you multiply by the index of refraction, and that is now the maximum, the peaks of your Fabry-Perot resonance. And then the minimums do the opposite. They're actually divided by the index of refraction. So the more refractive this material is, the more these peaks and valleys will get stretched away from each other. So again, you can think of that. So there's the equivalent length. So even though it's, say, 1 micron thick, if I'm at the trough of that resonance, it will be as if I only went through, say, a half a micron of material, even though I had that full micron. Or the opposite can be true. Even though it's 1 micron of material, if I get it just right at the resonance, it will be as if it went through 6 microns instead. So the Lambertian limit now, we're going to kind of do a rough derivation of this. And the way it works is you imagine a slab of material with Lambertian scattering happening at both sides. So I illuminate it from the top, and then it scatters every which way on this roughened surface, and there's no reflections. Then it propagates down to the bottom. And again, a bunch of it is going to scatter back away, and some of it is going to fall off the other end. What is the equivalent path length of this particular geometry here? So the first thing you do is you assume perfect Lambertian scattering, which you can quantify with a directivity profile of 4 times the cosine of theta. Fun fact. We're not going to derive that. If you take enough optics classes, this idea of specular reflection comes up a lot, and that cosine theta just represents what happens when you scatter off of a perfectly rough surface. So light comes in, and then it gets scattered every which way, and now we're just going to follow those rays and add them all up as they propagate from top to bottom. So that's what this integral here now does. So you imagine, say, here is this particular ray propagating through this tiny little solid angle at this angle here. So there's the directivity associated with that particular ray. And then this is the absorption of that ray as it propagates from top to bottom. So you see it's 1 minus this e to the minus a alpha w. And then the secant theta represents this. So at normal incidence, the secant theta is 1 and approaches infinity as you go to 90 degrees there. Okay, so that's the absorption of that particular ray weighted by its directivity. And then you have your Jacobian there. And we do the whole integral in polar coordinates. We're just adding up all of the energy. And that will tell me my absorption factor from top to bottom on that first pass. So then this is a very yucky integral. So we're going to do some hand wavy approximations. So first things first, we're going to assume that the film is very thin, meaning W is very small. And we're going to assume it is relatively low loss. So that alpha W term is going to be very, very tiny. So you can say, is this a valid assumption? Well, yeah, because if it was thick and high loss, we wouldn't care anymore because it would be absorbing it. So what you do is you apply the Taylor series expansion on some stuff and a few terms fall out. And you do a little bit of hand waving on your arguments here because that secant term wants to shoot to infinity, but then you weight it by this cosine, which brings it back to 0. And after you do all the math and everything falls out at the end. And what you find is that this total absorption on that first pass is approximately just 2 times alpha times W here. Okay, so it's as if I enhanced my path length by a factor of 2, basically, right? It went through a distance of 1 thickness, but I've got 2. This factor of 2 here comes out. But now you can also account for the fact that it's going to keep on bouncing up and up forever. So all I'm going to do is lose a little bit of energy out the bottom, and then we're going to repeat the cycle as it bounces back and forth infinitely many times. So you imagine a ray coming down and striking the bottom surface. How much of that light now leaks out the bottom before coming back up again? So it turns out there are some arguments in optics you can make where the light extraction efficiency, that LEE, is just proportional to the sine squared of the critical angle. So the more dense the dielectric is, the less energy I will lose here. And then you just apply a little bit of Snell's law and you find that I'm going to lose a factor of 1 over n squared on that transmission out the bottom of this slab here. And then the rest of that energy is now going to bounce back up the opposite way. So now you calculate, I had some absorption and then there will be some reflection back up again. So you notice the reflection is the incident minus the absorption scaled by my little bit of energy loss out the bottom. But again, we apply that approximation. This 2 alpha W is very small. So it's basically, this little guy here is 0. So this whole factor is very close to 1. So you can approximate it as this 1 minus 1 over n squared. So that is the reflected energy that comes back up again. And then you repeat the process into an infinite series. Okay, so the absorption in each little pass can be approximated by this summation here. And it's a geometric series that eventually converges to 2 alpha n squared W. So there's a little bit of approximation and hand waving going in there, but it's a very solid result. So then finally, I have some A, you calculate the equivalent path length with that. So you do some approximations to that natural log from 5 slides back, and you eventually find that the equivalent path length of this system, or sorry, then one last step, you add a mirror at the back contact, right? So initially we had an ARC at top and another at the bottom. So what if I just make it a mirror at the bottom here and I keep scattering with each reflection? So that adds a factor of 2. And then we apply that natural log term from several slides back. And so when all of the dust settles mathematically, you eventually find that the total equivalent path length of this thing is 4n squared W. So that same Jablonovich limit is sometimes also referred to as, quote, the 4n squared limit of path length enhancement. So for crystalline silicon, which has an index of refraction of about 3.5-ish, you multiply that by 4, or you square it and multiply by 4, and you find that you can get a path length enhancement of about 50 times. So a 1 micron slab of silicon, if treated correctly, can behave as if it is 50 microns thick. That's how you kind of describe the benefits here. So with that in mind, we went through all that trouble. Now let's think outside the box a bit. So this is one of my favorite little parts of the lecture is we went through all that work to do all that fun Lambertian scattering. What if I did some arrangement like the following? So you see what I've done is I've added a bunch of surface contacts here, right? So light bounces around, it has nowhere to go except for these little pieces here of green, where it's an anti-reflective coating, and I'm concentrating all of the light into it here, right? So I don't have to bother with any of that surface roughening. And you'll notice, like, it seems as though if I shrink this little green area very, very tiny, I can get essentially perfect light trapping. So why would I bother with all that goofy Lambertian stuff when I could just do a concentration like this? So it's fun to let that stew in the back of your mind for a bit, because this is one of the fun parts of doing engineering. Is it sounds like a great idea in theory, but then you have to ask, what are all the other things that have to come together in order to make this work? So one major problem is these big concentrators. It's like a big glass lens you'd have to put somewhere, which means it now has to be mounted. And it's this big, bulky, expensive thing, right? So yeah, I might get very good light trapping, but how expensive and nasty is it going to be to install all of these fixtures now on my solar cell? It doesn't help me much if I gain, 20% efficiency at the expense of 3 times the cost. Okay, so those are major issues you got to think about. Another major problem here is you now have to track the sun. Anytime you put a lens on this system to do concentration, if the sun moves, it just your focal point moves with it. So now your solar system has to follow the sun in order for this kind of idea to work. Okay, so that's one of the fun perks of the Lambertian limit is if I'm not, it doesn't really have to track the sun to get the same issue. Like the sun can move a little bit and I'm still trapping all the light. But if I over concentrate, the sun moves and my system shuts down. So not only do I need this big heavy lens to concentrate light, now I need all these mechanical servos to track the sun and remain aligned. So not only did I triple my cost, I just added like another triple on top of that. And then you have to ask yourself, okay, is this even really worth it at the end of the day? Because if hypothetically I had a perfect Lambertian system, I'm getting like 81% light trapping. So you have to think about this in terms of, even if I had absolutely perfect light trapping, the best I could do over the Lambertian limit is a 20% improvement. So if I add more than 20% cost in order to chase those extra photons, I've lost. I can't do any, it's not worth it. So there's a famous expression in business is don't spend dollars at the expense to chase pennies. Or you're chasing pennies at the expense of dollars. Okay, so yeah, I might get 100% light trapping efficiency, but this system here is already 80%. So the best I can do is a 20% improvement on top of that. So it better not cost more than 20% to get there. Okay, so you could also say, well, what if I just double the thickness? I go from 1 micron to 2. Now instead of 81%, I might go to 90 or say. So even there, so there's simple ways to stay within this paradigm that don't involve all these extra extravagant expenses. So kind of the moral of the story is there, just because someone says this is the absolute optimal light trapping you can get, there are certain assumptions that go with those kinds of statements that you have to be careful of. They're often very loaded statements. But then you also have to say, well, yeah, just because I could hypothetically do better, the amount of extravagance I have to invest in to get there is going to be horribly expensive oftentimes. So some sort of philosophical ideas to think about there. But that's everything I have on light trapping in a nutshell. So if you have any questions, I'll be happy to answer. Nobody.
Thanks, James. Yeah, I just wanted to reiterate, hopefully, those of you, the students, you were able to recognize the connection to some of the light trapping stuff we talked about, as well as the basic lecture on statistical optics. We have time for questions if there are any. Let's see, I didn't see any on chat, but.
So just a fun fact about this particular derivation I did is I haven't been able to find that exactly in the literature. Most people, when they do that derivation, they do these weird hand wavy things where they talk about the density of states for photons within this system. And I remember Mike Scarpella was sending out some group discussion on that. And I kind of like, as someone who's not a material scientist, I find I get kind of frustrated at that, because this feels a lot more just streamlined and intuitive to me to just follow the rays as they bounce around, because it also helps to really emphasize the assumptions that are going into this model there.
Yeah, so, I agree. Yeah.
Sometimes I think I should publish this because I can't actually find a reference that does this particular approach, even though it feels nice and intuitive. I'm sure somebody's maybe done out there, but that's
yeah, you should write it up and send it to Applied Optics, one of the OSA journals. Yeah, I can definitely give you some guidance if you need me to. Yeah, I'd say I recommend it. There is a lot of confusion, but there is also, I mean, the problems arise from this interface between geometrical optics and physical optics, which is kind of part of the challenge we have also looked at in this class. In the very beginning, we started with geometrical optics, which is a little bit easier to understand. But then you need to have a little bit of physical optics in order to deal with the diffraction and wave optical effects, because once you get to really small structures, as you would need for these, eventually in these sorts of light trapping, to explain all the light trapping effects, I think there's a gray area where the two theories actually meet. But in any case, yeah, that's a little bit outside the scope of our class. But I guess I have one quick question. Do you, maybe you can comment on this. Do you know, or are you aware of any solar cells that have commercialized some of these ideas?
That's a very good question. I have no idea, honestly.
Okay.
All I could, because I focused, my dissertation was all on just modeling this stuff and showing what could be done kind of through simulation. But then you go way back here and you ask, let's see if I find the slide. So here's an actual solar cell you can buy off of Amazon. In fact, I think, let's go back some more. There's one you can, the high efficiency one.
Yeah, so I'm fairly certain that this procedure of random texturizing the silicon surface is now pretty standard in most factories in China, because I've seen some of them. However, I think the vast majority of this is done in a random fashion. So there is very little theoretical understanding or optimization, as far as I know. Yeah.
Because I think 10 years ago, that wasn't necessarily the case either. Where they didn't incorporate a lot of the surface texturing issues. I know like they would use polycrystalline instead of just regular silicon. That was another thing. So bits of your solar cell would be good, but all those little junctions would be these recombination sites. So there's a lot more than just trapping the light. Like once you trap the light, there's this whole extra problem of how do I get that electron in the hole to reach the contacts?
We had a lecture on that also, a little bit, I suppose. Yeah, that's a semiconductor physics part of it. Of course, we need to, the optoelectronics, which is a combination of both optics and the semiconductor physics, is certainly of great importance. There is a small company spun out of UCSB, Santa Barbara, called, I can't remember, but there was an epitaxial thin film gallium arsenide company. Can't remember that name of the company, but they were trying to do something similar, but I'm not sure what happened to it. But yeah, it's definitely an open challenge, important challenge for sure. By the way, one of the interesting things that I learned recently is that there is a open call for solar cells for moon missions and Mars missions. So these are quite interesting because they have to, not only for the mission, but also to be deployed on the moon, because NASA has a 20-year plan to return for a permanent base on the moon. So we're looking at, solar panels for a permanent base. And clearly the requirements for such a solar panel is very different than what would be on Earth, because clearly there are many requirements, but one of the key requirements is the reduction of weight, because you need to launch it. To launch something costs, something like $10,000 per kilogram or something like that. So it's a pretty ridiculous number. So even with SpaceX.
Yeah, so that's a very important point. This entire discussion was motivated by how do I make just, I assume I have infinite real estate and I don't care about space or weight. How can I make a solar panel that's cheap? But if you don't care about that, you need efficiency in a small package. A lot of these assumptions just go right out the window.
Yeah, so this, by the way, for the students, it's also interesting to think about this, because of course this is relevant to the canvas, because you really think about what the value proposition is. Space did not used to be a big business, but now clearly it is with the advent of many launch companies. The cost of launch has gone down by orders of magnitude. So you can send up a satellite for something like $100,000. Which is a lot of money, but still compared to tens of millions of dollars, it's orders of magnitude less.
This little graph here assumes a single band gap, like a single PN junction. So I know, like, if you do multiple PN junctions, you can fight this a little bit. Having a direct band gap semiconductor rather than an indirect like silicon, that helps a lot.
So in that sort of a situation, for instance, for communication satellites, and which is a big business, obviously, with 5G and so on, clearly there's a need for very, very high efficiency. Efficiency at all costs, to some extent. Because if you're going to send something to Mars, it better be as efficient as possible. And the second requirement, of course, is self-cleaning, right? So because Mars and Moon doesn't have this problem, but in Mars you have huge dust storms.
So that's another great point.
How do you clean it?
The spectrum here, because Mars's atmosphere will maybe change some of these issues as well. So like at least the 1 kilowatt suddenly tanks. I think it's like 1/3. Do you know what the difference is on Mars and Earth in terms of just raw power density?
The insolation is about 10 times higher because it's closer to the sun, right?
On Earth?
On Earth, yeah.
Oh, okay. So you lose 90% just by being farther away.
But I think something like that. I don't remember exactly the top of my head, but yeah. But there was this giant storm that lasted for 6 months last year, if you people remember, and at that time the rover had to basically shut down because not because it couldn't work, it's just there was not enough sunlight for powering it, the electronics. Tara has a very important question on chat. Are solar cell textures usually randomized, or did that pyramid texture work better? James, do you have a comment?
My understanding is randomizing is technically better, but something like the pyramid tends to work really well anyway, but there's a lot of weird spectral issues that happen with the regularity if you're not careful.
Yeah, I can add, yeah, sorry, go ahead.
I think that's, I don't know if anyone's like specifically quantified that, because like with the terahertz stuff, we just did regular patterns on top of our LEDs using just like big rectangular bricks instead of like a pyramid in that. And yeah, I think it's like the sort of the difference between randomized is like technically ideal, but you know, a regular pyramid structure will be like 90% as good probably anyway, depending on your bandwidth and the sizes. But the answer is it's complicated. I guess it's not really a simple.
I can add to that a little bit. So the reason people use pyramidal structures is because crystalline silicon has 3 crystal directions. And one of those directions, 111 specifically, can etch faster than the other directions, which is why that if you wet etch silicon, the chemical wet etching process proceeds faster in one direction, straight down in the case of a 111 silicon, as opposed to the other plates. So that's why you end up with these naturally pyramidal structures. So those are naturally occurring just from the chemical etching process of crystalline silicon. So that's why pyramidal structures are used to be very popular, because they were easy to make and they work reasonably well. Now, the completely random structures have 2 problems. One is you need to generate, how do you make them? The simplest way to make them is to use polycrystalline silicon. So you have many crystal directions, so you're basically randomized. It's almost like amorphous. So the crystal directions are very randomly oriented. So the etch directions are random, so you end up with a random structure. However, the problem with random polycrystalline silicon, as James pointed out earlier, is that the efficiency of polycrystalline silicon is generally much lower than that of monocrystalline silicon because of losses at the crystal boundaries, where the electrons get trapped at the crystal boundaries. So this is a big problem, and that's why randomizing is from an optical perspective better, because you can show you will trap more light, the 4n squared that James derived today. But it's optoelectronically, from the electronics perspective, it's worse because of the crystal boundaries. So this is why this is not a very simple problem. You have to think about all the different things that is going on. But it's a very good question. Yeah. In fact, I would say it's an open challenge still. What is a good trade-off between all these, the light trapping geometries, manufacturing challenges, as well as semiconductor losses in the devices? It's a very complex engineering problem, actually. And of course, the problem is different for different materials. So we only talked about silicon. The question can also be asked for germanium or gallium arsenide or whatever, for the other thin film materials and so on. Very, very challenging problem, but lots of exciting research and development happening. Perfect. So I think if there are no more questions, we can end on time for a change. Usually we go a lot longer. So this is great. And again, if there are any questions, feel free to message me and I'll relay them on to James. Thank you, James. Appreciate it. We'll see you on Thursday. Take care, everyone. Bye-bye.